This problem is about an apple falling. Okay, let's see. I'm going to start with a sketch. And I'm going to pick an initial and a final moment. I'm going to say initial. That moment, I'm going to make that when the apple just begins to drop from the tree. Okay, so when the apple's at rest. The apple is at rest just as it begins to fall from tree. Okay, and then I'll make our final moment when the apple has fallen 0.5 meters. Okay, I'm going to sketch each of these moments and then put any relevant info. Let's see, I think here's my tree. Here's my apple, tree trunk, and some ground. Okay, let's see. At this moment, the velocity initial of the apple is 0. It's not moving yet. Let's see. I know the mass of the apple, 0.1 grams. Okay, our question is, what is the impulse the Earth exerts on it during the first 0.5 meters of its fall? So now let me draw this again, but it will have fallen 0.5 meters. All right, here's my tree. Okay, so now the apple is somewhere here. The displacement is 0.5 meters. And the question we want to know is, what was the impulse exerted by Earth? Okay, the symbol for impulse is J, but it's also the same thing as change momentum. So I think I'm going to write this as the change in momentum is question mark. Change in momentum is impulse. Anything else I need in this sketch? I think I need a reference frame. I think I'm going to call down the positive direction. Everything's moving down here, so that's kind of easy. All right. Next, I want to represent this. I think I'll make a momentum bar chart. I'm going to say that the... I need a system. My system will be the apple. That's it. And I already defined my initial and final moment. So I can say that the momentum of the apple initial plus any change in momentum will equal the momentum of the apple final. All right, initially this apple has no momentum. Finally, the apple does have momentum because it is falling, it's moving. So let's see, I think I'll give it 3 boxes of momentum here. Well, where did that momentum come from? Momentum is a conserved quantity. Something must have transferred momentum into the system. What happened is that Earth applied an impulse to the apple, which then gave the apple momentum. So the change in momentum should also be 3 boxes. And you know what? All that I just explained verbally, let me write it down as part of my explanation. Okay, the apple has no momentum initially. Because it's not moving. The apple has momentum in the final moment because it is moving. And then I think that I'll say that momentum and velocity have the same direction. Which is down. And then according to my reference frame, down is positive. Okay, what I can say is that the Earth applied an impulse to the apple, which gave the apple momentum. Okay, the Earth applied an impulse to the apple, which gave the apple momentum. Momentum is conserved, not constant here. Conserved means that we can track where the momentum went. Constant means the initial momentum equals the final momentum. Here, the initial momentum does not equal the final momentum. The Earth applied an impulse which transferred momentum into the system. Okay, so there's my explanation. I'm going to write an equation based on this bar graph. I can say that the change in momentum equals the momentum of the apple final. Notice my subscripts and that I'm being consistent with all this labeling. I can elaborate on this equation. Change in momentum equals force times change in time. That's what change in momentum is, which is also called impulse. The final momentum of the apple is the mass of the apple times the velocity of the apple final. Yeah. Okay. And let me put a little explanation here. I wrote my equation based on the bar graph. Or bar chart. All right, next, what are we solving for? We wanted to solve for the change in momentum. So let's see how we want to do this. We know the mass of the apple. That's good. We don't know for how long it fell. Oh, we do know the force that the Earth exerts on the apple, right? The force that the Earth exerts is mg. But I need to calculate something else. I'm either going to need to find the change in time or the final velocity of this apple. So I'm realizing I'm going to have to do a little bit of kinematics. I think to do that, I will draw a velocity time graph for this apple. Okay, the velocity time graph for this apple, the initial velocity of the apple is 0. It speeds up as it goes down. Down is a positive direction. So it'll look like this. And then, let's say I want to know how long it took to get to 0.5 meters. Well, I know if this was I know the area under a velocity time graph is displacement. This area is the displacement. I can write an equation for the displacement based on this graph. Let's see. I would say, I'll start with this. The area, that's a triangle. The area would be 1/2 base times height. The area is the displacement. The base of this triangle would be the time. The height of this triangle would be my change in velocity, or in this case, just the final velocity. I'll write as change in velocity. Okay, that's good. I do know the displacement. I want to know the time, but I don't know the change in velocity. But I do know another thing, though. I know that the slope of this graph is the acceleration. In fact, let me write this the other way. I think I'll write it like this. The acceleration is the slope of this graph. Okay. The acceleration is the slope. The slope would be the change in velocity, right? Rise over run over the time. Oh yeah, that is my definition of velocity. Let me put some vector symbols in all this too. I do know the acceleration of the apple. It's 9.8 meters per second down. So I wonder if I can rearrange this equation for change in velocity, and I would get that acceleration times time is the change in velocity. And you know what? Why don't I just plug that in over here? I'm going to plug this in over here. All right, so now let me rewrite this equation. I get that the displacement is 1/2 t times a t. Ah, that simplifies a bit. The displacement is 1/2 a t squared. Ah, this is starting to look like a kinematic equation that I know. Let's see. I know how far the apple fell. I know the acceleration, but I need to know the time. Let me rearrange for time. I'll multiply both sides by 2. Divide by the acceleration. And take the square root. That's what the time is. Okay, now I can figure out for how long this apple fell. So let me put some of the numbers in. The displacement of the apple was 0.5 meters. The acceleration of the apple was 9.8 meters per second squared. That's the time. Okay, if I punch all of this into a calculator, I end up getting, let's see. Okay, I get 0.319 seconds for the time. So that was a little bit of work that I did here. I need to explain what I did and why I did it. I used the velocity versus time graph to create equations to calculate how long it took the apple to fall 0.5 meters. I need this time to calculate the impulse exerted by Earth on the apple. Oof, okay. Now let's see. Impulse is the change in momentum, and I said, if I go back to this equation with my bar chart, now I do know what that change in time is. So I just have to do F times change in t, and I get the impulse. Let me write that down. Impulse. Okay, impulse is written as a J. Funny. Impulse equals the change in momentum, which is F times change in t. These are vectors. Now, let's see. The force that the Earth exerts is mg. I'll multiply that by change in time. The mass of the apple is 0.1 kilograms. Let me fix my sketch. G is 9.8 newtons per kilogram. The time I just found, it's 0.319 seconds. And let's see what we get if we multiply that out. Okay, I get 0.313, and my unit comes out to a Newton times a second. And that is the unit for impulse. Okay, and let me explain a bit and evaluate this answer here, okay? I calculated the impulse exerted by Earth on the apple by multiplying the force Earth exerts on the apple by the amount of time the force is exerted. Okay, cool. I got a positive answer, and I would say that the impulse is positive. Because it points down. Which is the same direction as the force. And I called down the positive direction. Okay, so I'm kind of mixing my explanation with evaluation here. The other thing I would note is that from unit analysis, I got a unit Newton times second. Which is the unit for impulse. You know what? I think that I might calculate this one other way to check my work. I found the impulse by doing force times delta t, but I could have also just found the final momentum of the apple. I wonder if I could do it that way to check my work. I think I'll write that here. I'll make this part of my evaluation. To check my work, I will solve this problem. One other way. I will calculate the final momentum of the apple, which equals the impulse exerted by Earth according to my momentum bar chart. All right, so let's do that. Impulse equals change in momentum, which is the same thing as the final momentum of this apple. The mass of the apple times the velocity of the apple final. Okay, so all I need is the mass of the apple and the final velocity of the apple to double check this. So let's see what I've got here and how I can do that. I know the mass of this apple. I need to find out what's the velocity of the apple when the displacement is 0.5 meters. So let me think how I want to do that. I made this velocity time graph. And I know the initial velocity of the apple. I know the acceleration of the apple. I found the time. You know what? Maybe I'll use the slope equation to do this. I think that I'll do that. I'm going to find the velocity of the apple. Oops. Let's change that color. Find the velocity of the apple using the slope equation. For the velocity versus time graph. Okay, I know, let's see, slope is rise over run. The slope is the acceleration. The rise is the change in velocity. The run is the time. And what I want is the change in velocity, which in this case will be the final velocity. So I can say that the time times the acceleration will give me my change in velocity. My vector sign's on there. Okay. So let me calculate what that comes out to. The time we found earlier, what was the time? Oh, 0.319 seconds. The acceleration was 9.8 meter per second squared. Okay, let me multiply that. Okay, I get 3.1 0.26 meters per second for my change in velocity. I'll do some unit analysis. That second went away. And because the initial velocity was 0, this would be the final velocity. This would be the velocity of the apple after dropping 0.5 meters. Okay. Now, let me plug this into my impulse equation. Ooh, let's put that here. Now, plug into impulse equation. All right. I said that my impulse equaled the mass of the apple times the velocity of the apple final. Okay. Let me put the numbers in. The mass of this apple was 0.1 kilograms. The velocity that I just found was 3.126 meters per second. If I put that into a calculator, oh, I just moved that decimal, and I get 0.3126 kilograms times meter per second. Let's see if that's what I calculated earlier for impulse. Yeah, I just rounded earlier. 0.313. Maybe I'll change that. So for this evaluation, I would say I solved this problem 2 different ways. I got the same answer. So I feel confident that this answer is correct. All right, I solved this problem 2 different ways. And got the same answer. So I think it's correct. Another thing that I would note about units, a Newton times a second is a kilogram times meter per second. So yeah, it is the same answer. Okay. There's my problem.